escuchan? Bueno. Chun.
You've seen.
Perfecto, se escucha.
Hi, my name's Greg Durrett. I'm really excited to introduce you to my course, Natural Language Processing. I'm an assistant professor in the Department of Computer Science here at UT Austin, and I've been working in the field of natural language processing for about 12 years now. And it's been a really exciting 12 years, and we've seen a progression all the way from linear models, things like classifiers, up through the latest and greatest systems like ChatGPT. So if you played around with ChatGPT, you know that it can do things like this. We can ask a question like, how many years after the start of the Revolutionary War did George Washington step down as president? And the system will do its computation, and it will produce this answer that has to look up these two dates and take the difference between them and figure out this number of years. So ChatGPT is a large neural network language model, but what's and greatest systems like ChatGPT. So if you've played around with ChatGPT, you know that it can do things like this. We can ask a question like, how many years after the start of the Revolutionary War did George Washington step down as president? And the system will do its computation, and it will produce this answer that has to look up these two dates and take the difference between them and figure out this number of years. So ChatGPT is a large neural network language model, but what's a language model? What kind of neural network is being used here? What can it be used for? How is it trained? These are all kinds of questions that you might have that are going to get answered in this course. So the goal is to start all the way from ML fundamentals like classification and then build up to the tools that we need to understand systems like ChatGPT. We're going to cover all of the methods that we need here, and we're also going to understand the applications that modern NLP research is used for. And we're going to give you the tools to understand how to take these systems and apply them to real-world problems, so when you're faced with something down the road, you know what to use. The lectures for this course are going to walk you through a lot of these different modeling details and show you how these are actually built from the ground up. Here's an example of what one of the lectures is going to look like. So their formula involves Q, K, and V, which are computed based on the kind of input embeddings like we've been doing, multiplying by these parameter matrices WQ, WK, and WV. And we take this softmax of Q times K transpose, so that we've all seen. And then there's one extra little step that they do here, which is they divide and rescale everything by square root of dk, which is the basically vector dimension that all of these inner products are happening in. It basically just has the effect of making the softmax less peak. It's not too important. And then they multiply by V here in order to get the output. So they're taking their attention matrix A and multiplying that by V. And so what they're getting as the output is a kind of weighted combination of V. In addition to the lectures, we also have a number of programming assignments which are designed to give you hands-on experience. You're going to be actually building these models basically from scratch in PyTorch, so you're going to understand all the pieces from the ground up, and you're also going to understand the data and how important that is in these processes. So a big emphasis of the course is going to be thinking about data. You can look at the syllabus in the course website for more details. I'm really excited to teach this course, and I hope to have you as a student. Thank you.
Okay.
Hello, my name is Greg Durrett. Welcome to Natural Language Processing. In this segment, we're going to talk about the overall outline of the course and the broad goals. So let's start with what the goal of natural language processing, or NLP as we're going to call it going forward, is. So NLP is about solving problems that require deep understanding of text. And I'm going to talk about deep understanding in contrast to shallow understanding, things like string matching or regular expressions that you might have learned in in earlier programming courses. And we want to understand a little bit about the kinds of things that we want to build that require this deep understanding and why they require that. So for example, we want to build systems that can talk to us, like dialogue systems, machine translation systems, automatic summarization systems, etc. And so, we'd like to be able to have a conversation with our phone that goes like this. Hey Siri, what's your favorite kind of movie? Just sort of conversational, right? And Siri says, I like superhero movies. And then you say, okay, what's come out recently? And Siri says, The Avengers. So we'd like to be able to have a conversation with a personal assistant like this, be able to have a back and forth and get some information out of it. And in order to do this, this system needs to be able to understand what we're saying, respond appropriately, and then in some cases be able to retrieve information, like for example, a list of movies that have come out recently. So why does this require deep understanding? Well, you're never going to be able to write down a whole big set of rules that are going to encapsulate all the possible flows that the dialogue might take, right? The system needs some way of recognizing what we're saying beyond just some kind of rules or templates, and then knowing how to respond to it. So translation is another great example of this. So here's a sentence in Chinese and a corresponding translation from Google Translate. So the interesting thing here is that you cannot just go along and translate the sentence word by word. In particular, in the first chunk here, the Political Bureau of the CPC Central Committee, that's this first segment, which is followed by July 30th, which is followed by hold a meeting in Chinese. That's roughly what we call glosses of those little phrases. And that's out of order with respect to how it's ordered on the English side. And so in this translation process, we actually need to look at the syntactic structure here, understand the kind of concepts being communicated, and be able to render them in the right surface order. We can't just apply a dictionary and go along kind of word by word. So again, we need this deep understanding here. And a final example I'll give is systems that extract information and answer questions. If you type when was Abraham Lincoln born into Google, something like the following is going to happen. We recognize that born means, okay, we've got a big database of people and names, and we need to map the idea of someone being born to like this birthday field in the database. That doesn't sound all that complicated, but once you get a large database with a whole bunch of different columns and many, many ways of asking about them, it actually becomes a fairly involved problem. And then we need to retrieve the right birthday from this database with some sort of computation. It gets even trickier. Trickier when you ask about things that aren't in a database. For example, how many visitor centers are there in Rocky Mountain National Park? Okay, you could theoretically have a database that stores this information, but I guarantee you Google does not. And so instead, what we need to do is retrieve some information from the web using something like Google Search, and then try to find a relevant snippet and answer the question based on that. So in this case, the third paragraph of the Wikipedia article has a sentence that tells us the park has a total of 5 visitor centers. And so we're going to learn techniques in this course that are going to allow us to understand this pipeline, how to retrieve this information and then answer questions based on these snippets. Okay, so this kind of tells you the sorts of things that we want to build, and I think gives you an idea of why these problems might be hard. So let's talk a little bit about the standard NLP methodology for doing this. So our starting point is text. In this course, we're always going to start with text rather than speech input. There's a whole ton of interesting work that does use speech, and in general, we're going to assume that if you wanted to use speech, you could run something like an off-the-shelf automatic speech recognition system first. All right. For the first part of the class, we're going to talk about a set of tools for producing text, what we call text analysis. And this is going to be layers of annotation on top of this text, like syntactic parses, understanding the syntactic structure of the text, co-reference resolution, understanding which pieces of the text refer to the same real-world concepts, entity disambiguation, figuring out what those concepts are, understanding the discourse structure. And so in general, we have a whole set of tools available that are going to allow us to understand a little bit more of this deep structure of text so we can start to get at some of these things that we want to do. And then that's going to enable us to do all these cool applications like summarize things, extract information, answer questions, identify sentiment, translate a bit about the standard NLP methodology for doing this. So our starting point is text. In this course, we're always going to start with text rather than speech input. There's a whole ton of interesting work that does use speech. And in general, we're going to assume that if you wanted to use speech, you could run something like an off-the-shelf automatic speech recognition system first. All right. For the first part of the class, we're going to talk about a set of tools for producing text, what we call text analysis. And this is going to be layers of annotation on top of this text, like syntactic parses, understanding the syntactic structure of the text, co-reference resolution, understanding which pieces of the text refer to the same real-world concepts, entity disambiguation, figuring out what those concepts are, understanding the discourse structure. And so in general, we have a whole set of text refer to the same class. We're going to talk that if you wanted to use speech, you could run something like an off-the-shelf automatic speech recognition system first. All right. For the first part of the class, we're going to talk about a set of tools for producing text, what we call text analysis. And this is going to be layers of annotation on top of this text, like syntactic parses, understanding the syntactic structure of the text, co-reference resolution, understanding which pieces of the text refer to the same real-world concepts, entity disambiguation, figuring out what those concepts are, understanding the discourse structure. And so in general, we have a whole set of tools available that are going to allow us to understand a little bit more of this deep structure of text so we can start to get at some of these things that we want to do. And then that's going to enable us to do all these cool applications like summarize things, extract information, answer questions, identify sentiment, translate the text into another language, etc. And so throughout this course, we're going to tackle all of these all of these problems with the, under the kind of broad umbrella of statistical approaches using machine learning. All of these things require dealing with complex open domain text, and the only way we know to reliably do that is to learn models from large-scale data. All right, so let's talk about how we represent language. So in this kind of first text analysis piece, what do these representations look like? So we're going to start off the course by thinking about labels. So for example, if we say the movie was good, it's going to have a discrete sentiment label that's just going to say this is positive sentiment. We might have a statement like Beyonce had one of the best videos of all time. This is subjective. We might classify statements as subjective versus objective. All right, and there's a whole bunch of other different types of labeling schemes we might use. Another layer of annotation looks like either sequences or tags. And this is where we're going to go after labels. We're going to start to look at text as a structured object. And we want to be able to recognize that, in this case, this span Tom Cruise is a person and Mission Impossible is a work of art. And this is a task called named entity recognition. We're also going to look at things like part-of-speech tagging that analyze text sequentially. And from there, we're going to move on to tree structure. So this is really one of the distinguishing features of language, is the fact that it has this recursive hierarchical syntactic structure. And so we're going to understand what parse trees, like the one here, look like, and how to understand them and how to predict them. We're also going to look at semantic representations like lambda calculus here. This is another sort of tree structure that builds an expression to represent this idea of flights to Miami, which could be executed against a database. So taken together, this is going to give us a set of tools for understanding these different structures of language. And for each tool, we're going to see what machine learning techniques allow us to predict it and deal with it. All right, so now we've got these representations. How do we actually use them for these downstream applications? So we're going to zero in here on the case of trees, and I'm just going to give you a brief flavor for how this kind of thing is going to come up. So early in the course, when we think about feature-based linear models, one thing that trees might allow us to do is to extract some sort of syntactic feature for classification. Later, when we think about neural networks, a cool thing you can do with trees is actually build your neural network to have some sort of tree structure. And when we think about machine translation, one thing we might do is actually model the translation process as a mapping from a syntactic parse in one language to a syntactic parse in another language. And this is the model to do that is something called a tree transducer. So there's a whole bunch of ways that these analyses of text can impact our modeling. Of course, the elephant in the room is that with the rise of deep learning and neural networks, there's an increasing trend towards building purely end-to-end models. And so there's going to be this tension throughout the course of, do we use these intermediate pieces of text analysis or do we build models strictly end-to-end? And the answer is not going to be clear-cut. There have been huge successes from purely end-to-end models, but there's also a lot of interesting kind of cutting-edge work right now that is starting to move them back towards incorporating this kind of discrete structure for reasons of interpretability or controllability. And so this is a topic that's going to come up again and again throughout the course. So we have to think about also why any of these predictions is hard. So, I mentioned that we're going to need to build some sort of statistical models for mapping both from text to these analysis layers and then also going from the analysis layers to the applications. And the reason this is hard is because language is complicated and language is ambiguous. And so in order to understand that a little bit more, we're going to talk about what ambiguities we need to resolve and what ambiguity means in this context. All right, so we can look at a sort of apocryphal headline here. Teacher strikes idle kids. All right, so this is kind of funny, at least it's funny to me, because there's two interpretations of it. And despite the fact that when we look at this, we probably know what the author meant, we still get this other reading. So what the author probably meant was that teacher is a noun and strikes is a noun. Idle is a verb. This is a sort of unusual usage of it. And then kids is a noun. OK, but you could also read it as teacher is a noun, strikes is a verb, idle is an adjective, and kids is a noun. And so the second interpretation, of course, is that the teachers are really fed up with these kids who are idle and just pow. And so I talked about sequential analysis and part-of-speech tagging, which we're going to see early on in this course. And that's essentially about resolving which interpretation of the sentence we want to get. All right. Ban on nude dancing on governor's desk. All right. So we can think about this in the context of the last example. Like, what are the parts of speech here? It turns out that actually the parts of speech aren't really that ambiguous in this case. What's ambiguous is the syntactic structure. What the author intended is that we have two prepositional phrases here. We have a ban that is on nude dancing, and that ban on nude dancing is on the governor's desk. But the sort of funny interpretation is that we actually have this noun phrase concept of nude dancing taking place on the governor's desk. OK, they would probably want to ban that too, but that's neither here nor there. So the ambiguity in this case is a higher level syntactic one of how these different pieces compose. It's not a low level part of speech ambiguity, but instead one that we're going to have to understand syntactic parsing in order to deal with. All right, and let's look at a third example. Iraqi head seeks arms. Actually, in this case, we don't have either of these ambiguities. The parts of speech are totally clear, and the syntactic structure, it turns out, is clear as well. What is ambiguous is the sense of the word head. Is it someone's head, or is it like a head of state? And then similarly for arms, is it someone's arms, or are we talking about weapons here? So in this case, we have more of a semantic ambiguity that arises from the different senses of these words. Okay, so what we've seen here is that there are a bunch of these sort of binary ambiguities, right? There's two possible interpretations of something, and we need to pick between them. And this is what statistical models are going to allow us to do. And the reason NLP is hard is not because there's two possibilities, but actually because there's an exponentially large number of them. And so we're going to need really powerful models in order to reject all of those bad possibilities. So we're going to think about a translation example here. Il fait vraiment beau, which roughly means it's really nice out, or it's really nice, or the weather is beautiful. There's actually lots of different valid translations of this. But if we think about, even for this 4-word sentence, what could happen? It is really beautiful outside. That's another possibility. If you go word by word and translate this, he makes truly beautiful, this is actually something that is totally valid translations of each of those 4 words. Of course, it absolutely does not make sense and is not what the speaker or writer of this intended. Or in fact, actually handsome, another case. So a lot of times when we look at these examples of ambiguity and we say, oh, haha, there's 2 interpretations. No, in fact, there's billions of interpretations, and we're going to need structured models that can reason about them, and again, are very statistically powerful so they can pick the right one out of all of these possibilities. Okay, so in order to understand those kind of models and situate what we're going to be looking at with respect to history, we're just going to take a very quick cruise through the timeline of NLP. So our timeline is going to start. So we start with different senses of these words. We're just going to take a very quick cruise through the timeline of NLP. So our timeline is going to start in the 80s, late 80s, with the so-called AI winter. And so systems at this time were largely non-statistical. They were either rule-based or expert systems. And so the history of AI has been about there's progress, and then there's periods where we sort of hit a wall, and then progress happens again. And so this was one of those periods of cooling off where there was less interest, sort of a wall was hit. In the early 90s, researchers at IBM did some of the earliest work on statistical machine translation using the proceedings of the Canadian Parliament, which was a whole bunch of aligned data, so sentences that were, in this case, in French and English, that corresponded to each other, and they were able to build a statistical translation system out of that. So this, as well as the development of the Penn Tree Bank in 1993, which was one of the first large-scale corpora annotated with syntactic information, are 2 of the sort of first instances of well-known, successful statistical modeling efforts. And so the Penn Tree Bank, once that data set existed, started leading to people building things like part-of-speech taggers and syntactic parsers and saying, oh, hey, wait, it looks like having all this data is actually useful. And so then this led to an explosion of interest in things like supervised learning, support vector machines, conditional random fields, applied to tasks like name identity recognition or sentiment analysis. So we started to understand that data was really useful, and machine learning could help us harness the power of that data to solve some of these problems. There's a lot of interest also in unsupervised learning, things like topic models and grammar induction. We're not going to talk about these so much in the course. They sort of ended up kind of falling off in terms of the overall interest in them. People started becoming more interested in, okay, how do we combine labeled and unlabeled data? And then this led to, in 2014, 2015, the neural revolution. And then following that, the kind of revolution in pre-trained models we've seen with things like BERT and GPT. So those models are great at this task of harnessing all the data on the web, as well as whatever supervised corpus you have for the task that you want to solve. And so this, what's here in this box, is the techniques that are going to be the focus of this course. So we're going to focus on supervised learning, semi-supervised methods, and neural network models. And the kind of common thread of all these models is that they're going to be able to handle ambiguity by learning how to map from input text to linguistic representations using data. And that's going to allow us to start to tackle these issues that we saw. That we saw in the previous few slides. So to just give a brief sense of where we're going in the outline of the rest of the course, we're going to start by talking about classification. We'll start with linear classification and then very quickly move into neural and talk about word representations, which is a really important kind of ingredient for how to actually take string-valued language data and convert it into something that machine learning can use. Then we're going to talk about these text analysis tasks like tagging and parsing, and we're going to talk about the structured models that can deal with these tasks. Then we'll talk about language modeling and pre-training. So once we've seen this, we really need to kind of build up the idea of language models, which are going to establish the idea of recurrent neural networks and things like that for sequentially predicting text. And then pre-trained models are going to inform how we think about building models for the course going forward. We'll then go into question answering and semantics, machine translation, and other applications. We're going to kind of see how those core tools and models can then be built out to solve all of these different problems, and sort of brief tour of what the state of the art looks like in each of these areas. So that's where we're headed, and that's it for this segment. In this segment, we're going to talk about the simplest machine learning models that we're going to see in this course, which are linear binary classifiers. So these may be something that you've come across in a previous course. So consider this a way to kind of establish notation for this and just to make sure we're all on the same page. So what a classifier is roughly going to do is it's going to take as input a point x in R to the d. This means some sort of numeric data in a d-dimensional real-valued feature space. And we are going to also use the notation f of x extensively in this course, where f is what we call a feature extractor. All right, and so the reason we think about it this way is that x in a lot of our problems is going to be a string. It's not going to be a numeric valued thing, and then f of x is going to be the set of features in the d-dimensional space. So we might move back and forth between these two different notations at various points throughout the course, but generally there does need to be some process of mapping from, again, a string input, which most natural language varying. Reason we think about it this way is that x in a lot of our problems is going to be a string. It's not going to be a numeric valued thing, and then f of x is going to be the set of features in the d-dimensional space. So we might move back and forth between these two different notations at various points throughout the course, but generally there does need to be some process of mapping from, again, a string input, which most natural language is, into some sort of numeric representation that can be used in machine learning. All right, and then each point has a label, y, and in binary classification, there's only going to be two possibilities. And we're going to refer to these as -1 and +1, or negative and positive class. So roughly, the way we can think about this is that we've got a set of points. This is going to be a two-dimensional feature space. Roughly going, again, a string input, which most natural language is, into some sort of numeric representation that can be used in machine learning. All right, and then each point has a label, y, and in binary classification, there's only going to be two possibilities. And we're going to refer to these as -1 and +1, or negative and positive class. So roughly, the way we can think about this is that we've got a set of points. This is going to be a two-dimensional feature space. And we're going to draw some pluses up here, and we're going to draw some minuses down here. And so each of these, again, represents one of these x's, and then whether it's plus or minus represents the label. All right, and then we're going to represent a classifier as a weight vector w. And you might see theta in some places, such as texts or academic papers. We're going to try to stick with w in this course, but again, these mean the same thing. And so the way that this weight vector leads to a classification decision is the following. We compute the dot product, or the kind of vector transpose here, of the weights and the features associated with the point. And then we ask, the leads to a classification decision is the following. We compute
Salud. Gracias. Es una verga, boludo, ChatGPT. No te deja...
¿Cómo?
Boludo, a mí me desapareció. Esto me pasó desde ayer.
¿Qué se desapareció?
Para editar la pregunta. ¿Cómo edito la pregunta?
Cuando está todavía, o sea, cuando está generando la respuesta
No, editar la pregunta, boludo.
Sí, así. A mí me pasa que tenés que esperar que termine de
Ya
tirarte todo para que editarla. Capaz que se trabó en eso.
No, ya terminó y esto me está pasando de ayer. Le hago refresh, todo, ¿no?
Qué raro, hola, yo en la Mac lo usé bien, eso. Edité bastante.
Acá no. Y acá no.
Gracias, GPT, ¿por qué pasa eso?
Sí, ¿no? Este sí, acá sí. No, el primero no. El primero no.
¿No?
No. El segundo ya sí. Raro. Puesta en otra forma.
Compute the dot product, or the kind of vector transpose here, of the weights and the features associated with the point, and then we ask if that's greater than 0. And essentially, the way we can think about this is that there's the weight vector points in some direction in this feature space, and then we've got this decision boundary that's perpendicular to the direction that W is pointing. So the way to think about this is any point on the top right side of this decision boundary is going to be classified as positive because the dot product with W is going to be positive. Any point on the other side of the boundary is going to be negative. And you know, we're not going to worry too much about what happens if you exactly land on the boundary. You need to break ties somehow. All right, so that's the basics of the kind of formulation of linear binary classification. One thing I will note is that we often see in kind of other settings here, we see a bias term B, and we are going to not use that. And the reason is because we can just take f of x, which, you know, let's say the features for a particular point are something like this, and we transform this into an f of x that has a 1 on the end of it. So by adding a 1 to the end, we've basically folded this bias term into into the actual feature vector, and so that's what's going to allow us to stick with this representation of a classifier going forward, and we're not going to have to juggle these bias terms. So this is the kind of basic setup of binary classification. Going forward over the next few segments, we're going to talk about the perceptron and logistic regression, which are two different ways of thinking about learning these weights that we're going to see are functionally quite similar. So that's it for this segment.
Sailing on a boat headed towards StatQuest. Join me on this boat, let's go to StatQuest. It's super cool. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about linear regression, aka General Linear Models Part 1. There's a lot of parts to linear models, but it's a really cool and powerful concept, so let's get right down to it. I promise you, I have lots and lots of slides that talk about all the nitty-gritty details behind linear regression, but first, let's talk about the main ideas behind it. The first thing you do in linear regression is use least squares to fit a line to the data. The second thing you do is calculate r squared. Lastly, calculate a p-value for r squared. There are lots of other little things that come up along the way, but these are the three most important concepts behind linear regression. In the StatQuest, fitting a line to data, we talked about fitting a line to data. Duh. But let's do a quick review. I'm going to introduce some new terminology in this part of the video, so it's worth watching even if you've already seen the earlier StatQuest. That said, if you need more details, check that StatQuest out. For this review, we're going to be talking about a data set where we took a bunch of mice and we measured their size and we measured their weight. Our goal is to use mouse weight as a way to predict mouse size. First, draw a line through the data. Second, measure the distance from the line to the data, square each distance, and then add them up. Terminology alert. The distance from the line to the data point is called a residual. Third, rotate the line a little bit. With the new line, measure the residuals, square them, and then sum up the squares. Now rotate the line a little bit more. Sum up the squared residuals, etc., etc., etc. We rotate, and then sum up the squared residuals. Rotate, then sum up the squared residuals. Just keep doing that. After a bunch of rotations, you can plot the sum of squared residuals and corresponding rotation. So in this graph, we have the sum of squared residuals on the y-axis and the different rotations on the x-axis. Lastly, you find the rotation that has the least sum of squares. More details about how this is actually done in practice are provided in the stat quest on fitting a line to data. So, we see that this rotation is the one with the least squares, so it will be the one to fit to the data. This is our least squares rotation superimposed on the original data. Bam! Now we know why the method for fitting a line is called least squares. Now we've fit a line to the data. This is awesome! Here's the equation for the line. Least squares estimated 2 parameters. A y-axis intercept, and a slope. Since the slope is not 0, it means that knowing a mouse's weight will help us make a guess about that mouse's size. How good is that guess? Calculating r² is the first step in determining how good that guess will be. The stat quest, r² explained, talks about, you got it, r². Let's do a quick review. I'm also going to introduce some additional terminology, so it's worth watching this part of the video even if you've seen the original stat quest on r². First, calculate the average mouse size. Okay, I've just shifted all the data points to the y-axis to emphasize that, at this point, we are only interested in mouse size. Here, I've drawn a black line to show the average mouse size. Bam! Now, sum the squared residuals. Just like in least squares, we measure the distance from the mean to the data point and square it, and then add those squares together. Terminology alert. We'll call this SS mean, for sum of squares around the mean. Note, the sum of squares around the mean equals the data minus the mean squared. The variation around the mean equals the data minus the mean squared divided by n. N is the sample size. In this case, n equals 9. The shorthand notation is the variation around the mean equals the sum of squares around. Squares around the mean divided by n, the sample size. Another way to think about variance is as the average sum of squares per mouse. Now go back to the original plot and sum up the squared residuals around our least squares fit. We'll call this SS fit for the sum of squares around the least squares fit. The sum of squares around the least squares fit is the sum of the distances between the data and the line squared. Just like with the mean, the variance around the fit is the distance between the line and the data squared divided by n, the sample size. The shorthand is the variation around the fitted line equals the sum of squares around the fitted line divided by n, the sample size. Again, we can think of the variation around the fit as the average of the sum of squares around the fit for each mouse. In general, the variance of something equals the sum of squares divided by the number of those things. In other words, it's an average of sum of squares. I mention this because it's going to come in handy in a little bit, so keep it in the back of your mind. Okay, let's step back a little bit. This is the raw variation in mouse size. And this is the variation around the least squares line. There's less variation around the line that we fit by least squares. That is to say, the residuals are smaller. As a result, we say that some of the variation in mouse size is explained by taking mouse weight into account. In other words, heavier mice are bigger, lighter mice are smaller. R² tells us how much of the variation in mouse size can be explained by taking mouse weight into account. This is the formula for R² size. Fit as the average of the sum of squares around the fitted line divided by n for each mouse. In general, the variance of something equals the sum of squares divided by the number of those things. In other words, it's an average of sum of squares. I mention this because it's going to come in handy in a little bit, so keep it in the back of your mind. Okay, let's step back a little bit. This is the raw variation in mouse size. And this is the variation around the least squares line. There's less variation around the line that we fit by least squares. That is to say, the residuals are smaller. As a result, we say that some of the variation in mouse size is explained by taking mouse weight into account. In other words, heavier mice are bigger, lighter mice are smaller. R² tells us how much of the variation in mouse size can be explained by taking mouse weight into account. This is the formula for R². It's the variation around the mean minus the variation around the fit divided by the variation around the mean. Let's look at an example. In this example, the variation around the mean equals 11.1, and the variation around the fit equals 4.4. So we plug those numbers into the equation. The result is that R² equals 0.6, which is the same thing as saying 60%. This means there is a 60% reduction in the variance when we take the mouse weight into account. Alternatively, we can say that mouse weight explains 60% of the variation in mouse size. We can also use the sum of squares to make the same calculation. This is because when we're talking about variation, everything's divided by n, the sample size. Since everything's scaled by n, we can pull that term out and just use the raw sum of squares.
In this case, the sum of squares around the mean equals 100, and the sum of squares around the fit equals 40. Plugging those numbers into the equation gives us the same value we had before, r squared equals 0.6, which equals 60%. 60% of the sums of squares of the mouse size can be explained by mouse weight. Here's another example. We're also going to go back to using variation in the calculation, since that's more common. In this case, knowing mouse weight means you can make a perfect prediction of mouse size. The variation around the mean is the same as it was before, 11.1, but now the variation around the fitted line equals 0 because there are no residuals. Plugging the numbers in gives us an r squared equal to 1, which equals 100%. In this case, mouse weight explains 100% of the variation in mouse size. Okay, one last example. In this case, knowing mouse weight doesn't help us predict mouse size. If someone tells us they have a heavy mouse, well, that mouse could either be small or large with equal probability. Similarly, if someone said they had a light mouse, well, again, we wouldn't know if it was a big mouse or a small mouse because each of those options is equally likely. Just like the other two examples, the variation around the mean is equal 11.1. However, in this case, the variation around the fit is also equal 11.1. So we plug those numbers in and we get r squared equals 0, which equals 0%. In this case, mouse weight doesn't explain any of the variation around the mean. When calculating the sum of squares around the mean, we collapse the points onto the y-axis just to emphasize the fact that we were ignoring mouse weight. But we could just as easily draw a line, y equals the mean mouse size, and calculate the sum of squares around the mean around that. In this example, we applied r squared to a simple equation for a line, y equals 0.1 plus 0.78 times x. This gave us an r squared of 60%, meaning 60% of the variation in mouse size could be explained by mouse weight. But the concept applies to any equation, no matter how complicated. First, you measure, square, and sum the distance from the data to the mean, then measure, square, and sum the distance from the data to the complicated equation. Once you've got those two sums of squares, just plug them in and you've got r squared. Let's look at a slightly more complicated example. Imagine we wanted to know if mouse weight and tail length did a good job predicting the length of the mouse's body. So we measure a bunch of mice. To plot this data, we need a three-dimensional graph. We want to know how well weight and tail length predict body length. The first mouse we measured had weight equals 2.1, tail length equals 1.3, and body length equals 2.5. So that's how we plot this data on this 3D graph. Here's all the data in the graph. The larger circles are points that are closer to us and represent mice that have shorter tails. The smaller circles are points that are further from us and represent mice with longer tails. Now we do a least squares fit. Since we have the extra term in the equation representing an extra dimension, we fit a plane instead of a line. Here's the equation for the plane. The y value represents body length. Least squares estimates three different parameters. The first is the y-intercept. That's when both tail length and mouse weight are equal to 0. The second parameter, 0.7, is for the mouse weight. The last term, 0.5, is for the tail length. If we know a mouse's weight and tail length, we can use the equation to guess the body length. For example, given the weight and tail length for this mouse, the equation predicts this body length. Just like before, we can measure the residuals, square them, and then add them up to calculate r squared. Now, if the tail length, or the z-axis, is useless and doesn't make the sum of squares fit any smaller, then least squares will ignore it by making that parameter equal to 0. In this case, plugging the tail length into the equation would have no effect on predicting the mouse size. This means equations with more parameters will never make the sum of squares around the fit worse than equations with fewer parameters. In other words, this equation, mouse size equals 0.3 plus mouse weight plus flip of a coin plus favorite color plus astrological sign plus extra stuff, will never perform worse than this equation, mouse size equals 0.3 plus mouse weight. This is because least squares will cause any term that makes sum of squares around the fit worse to be multiplied by 0 and, in a sense, no longer exist. Now, due to random chance, there is a small probability that the small mice in the dataset might get heads more frequently than large mice. If this happened, then we'd get a smaller sum of squares fit and a better r squared. Wah wah, here's the frowny face of sad times. The more silly parameters we add to the equation, the more opportunities we have for random events to reduce sum of squares fit and result in a better r squared. Thus, people report an adjusted r squared value that, in essence, scales r squared by the number of parameters. R squared is awesome, but it's missing something. What if all we had were two measurements? We'd calculate the sum of squares around the mean, in this case, that would be 10. Then we'd calculate the sum of squares around the fit, which equals 0. The sum of squares around the fit equals 0 because you can always draw a straight line to connect any 2 points. What this means is when we calculate r squared by plugging the numbers in, we're going to get 100%. 100% is a great number. We've explained all the variation, but any 2 random points will give us the exact same thing. It doesn't actually mean anything. We need a way to determine if the r squared value is statistically significant. We need a p-value. Before we calculate the p-value, let's review the main concepts behind r squared one last time. The general equation for r squared is the variance around the mean minus the variance around the fit divided by the variance around the mean. In our example, this means the variation in the mouse size minus the variation after taking weight into account divided by the variation in mouse size. In other words, r squared equals the variation in mouse size explained by weight divided by the variation in mouse size without taking weight into account. In this particular example, r squared equals 0.6, meaning we saw a 60% reduction in variation once we took mouse weight into account. Now that we have a thorough understanding of the ideas behind r squared, let's talk about the main ideas behind calculating a p-value for it. The p-value for r squared comes from something called f. F is equal to the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. The numerators for r squared and for f are the same. That is to say, it's the reduction in variance when we take the weight into account. The denominator is a little different. These dotted lines, the residuals, represent the variation that remains after fitting the line. This is the variation that is not explained by weight.
So together, we have the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. Now let's look at the underlying mathematics. Just as a reminder, here's the equation for r squared. This is the general equation that will tell us if r squared is significant. The meat of these two equations are very similar and rely on the same sums of squares. Like we said before, the numerators are the same. In our mouse size and weight example, the numerator is the variation in mouse size explained by weight. And the sum of squares around the fit is just the residuals squared and summed up around the fitted line. So that's the variation that the fit does not explain. These numbers over here are the degrees of freedom. They turn the sums of squares into variances. I'm going to dedicate a whole stat quest to degrees of freedom, but for now, let's see if we can get an intuitive feel for what they're doing here. Let's start with these. P fit is the number of parameters in the fit line. Here's the equation for the fit line in a general format. We just have the y-intercept plus the slope times x. The y-intercept and the slope are two separate parameters. That means p fit equals 2. P mean is the number of parameters in the mean line. In general, that equation is y equals the y-intercept. That's what gives us a horizontal line that cuts through the data. In this case, the y-intercept is the mean value. This equation just has one parameter. Thus, p mean equals 1. Both equations have a parameter for the y-intercept. However, the fit line has one extra parameter, the slope. In our example, this slope is the relationship between weight and size. In this example, p fit minus p mean equals 2 minus 1, which equals 1. The fit has one extra parameter, mouse weight. Thus,
¿Todo tranqui?
Todo bien, boludo.
¿La estás pasando mal?
Sí. Estoy pensando algo.
¿Sabes cómo te... Se me ocurrió algo. ¿Sabes cómo puedes pensar mejor?
¿Con qué? Y justamente pude. ¿Sabes cómo te puedo ayudar a enfocarte mejor?
No sé, el que está en problemas sos vos, yo no me quiero...
Yo estoy en problemas, yo estoy
O sea,
pensando, amigo.
ahora estoy intentando ser más empático, ¿viste?
Parece
Entonces
que
quiero preocuparme por vos y yo lo que yo sienta no importa.
tu empatía funciona
Vos,
mal, me parece.
acá ahora el foco de atención sos vos. Hace, dale. Pasá. Lo de yo, picón.
¿Qué?
Lo de yo. ¿En qué? ¿Cuál es el problema?
No, ¿cómo es? El problema es que me estoy haciendo problemas yo usando, viste, es como que estoy... Siento, boludo, que... Viste que tenemos el coso, el AI que te da Berserk, que es una librería, es un SDK. Siento que tiene todo, viste. Entonces si vos lo sabés usar, haces y así, y haces todo. Pero como yo no sé usar un par de cosas, me estoy acomodando y estoy haciendo cagadas, se me hace.
Pero cagadas como.
No, no es que cagadas, sino que no lo estoy usando correctamente, ¿viste?
Ok.
Entonces, estoy haciendo cosas que quizás tiene integrado esto para hacerlas mejor, las estoy haciendo por fuera,
Sí.
y tengo que acomodarlas a lo que sé usar de esto, de este SDK.
O sea, ya hiciste cosas
Claro,
y vos querés, en vez de dejar esas cosas, utilizar las que ya están hechas en Berserk. ¿Eso?
No, hice cosas trabajando sobre Vercel,
Sí.
que debería ser cosas trabajando con Vercel, no sobre Vercel.
Pero claro, o sea, yo estoy hablando de la SDK, o sea, o sea, vos hiciste tu propia versión y vos querés usar el SDK.
Estoy haciendo, no, lo estoy
No entiendo
usando,
qué es en Vercel y sobre Vercel, no entiendo a qué te referís con eso.
estoy usando el SDK,
Sí.
pero tengo entendido que te tira un montón de funciones, un montón de callbacks que no estoy usando, ¿viste? Entonces lo estoy haciendo todo como por mi cuenta.
Sí.
Y ahí después esas cosas que hago tengo que acomodarlas al SDK, entonces como que funciona pero medio mal.
Claro.
A eso voy yo. No, o sea, funciona, pero no está, no me gusta, quiero decir, nada.
No te tiene por qué gustar.
Sí,
O sea, quiero decir, tenés razón, pero eso lo haces en la siguiente.
sí, sí.
O sea, tampoco, o sea, una vez ya si lo programaste y funciona, a veces hay que decir, ok, pues me voy a tener que quedar con este código de mierda y seguir. Sobre todo ahora, porque es como, yo lo que diría es, hacer como puedas, tipo, no reinventes la rueda, tipo, lo que sé que ya escribiste, está. O sea, que escribiste y funciona, ¿no? Si cumple esa cosa, ya está, se queda ahí. Entiendo que no es lo mejor, entiendo que es feo, entiendo que incluso hasta te puede romper las pelotas en otros casos, pero es mejor tenerlo allí, o sea, dejarlo, trabajar sobre eso, ¿no? Y terminarlo. Y después si eso, después, cuando hayas, a lo mejor puedes hacer otro, vas a hacer otro proyecto, vas a estar trabajando más, sea lo que sea, conforme vaya pasando el tiempo vas a ganar más conocimientos al respecto. Entonces, en otro momento podés volver, verlo y
Sí,
decir,
después,
hey, quiero rehacerlo.
después hago otro.
Pero ahora mismo eso se llama premature optimization. O sea, ya está, ya lo hiciste, no hace falta optimizarlo más porque esto que lo otro ya está. Tipo, aprende a soltar.
Claro,
Es eso, o sea, porque te tarda más tiempo en hacerlo, el hacerlo bien, te va a hacer tardar 10 veces más que solamente que funcione. ¿Entendés? El objetivo es que primero y principal que funcione. Después funcione, vamos a hacerlo bien, hacerlo lindo, pero primero que funcione. Sobre todo en tu posición, en la posición en la que estás. Si sos un senior developer, manager, no sé qué chota, bueno, a lo mejor se te puede pedir un poco más y que no, que esto, que lo otro. Pero who cares? El objetivo es que funcione. Después vemos, te arreglo los problemas. Entonces no trates de. Si lo hiciste por tu cuenta y entonces conectarlo a Vercel y ya está, ¿me entendés?
sí, sí, ya sé, boludo, pero bueno. Cuestión de. Que quede, que la onda es que quede razonablemente bien. Y bueno, todavía no estoy cerquita. Pero estoy, por eso digo, estoy pensando porque no sirve de nada pegarme el cabezazo con el teclado y ver qué onda. Entonces por eso.
Y hay otra parte de la feature en la que puedas trabajar. Por lo mejor, tipo, hay otra parte de la aplicación, otra feature de la aplicación en la que puedas trabajar. Por lo mejor decir, hey, esto, voy a poner un pin, queda acá y me voy a otra cosa.
Puede ser.
O sea, tratar de trabajar en otra funcionalidad, así te olvidas de esta funcionalidad y después volvés.
Puede ser, puede ser, puede ser.
Think about it.
¿Mm?
Think about it.
in this segment, we're going to talk about the simplest machine learning models that we're going to see in this course, which are linear binary classifiers. So these may be something that you've come across in a previous course. So consider this a way to kind of establish notation for this and just to make sure we're all on the same page. So what a classifier is roughly going to do is it's going to take as input a point x in R to the d. This means some sort of numeric data in a d-dimensional real-valued feature space. And we are going to also use the notation f of x extensively in this course, where f is what we call a feature extractor. All right, and so the reason we think about it this way is that x in a lot of our problems is going to be a string. It's not going to be a numeric valued thing, and then f of x is going to be the set of features in the d-dimensional space. So we might move back and forth between these two different notations at various points throughout the course, but generally there does need to be some process of mapping from, again, a string input, which most natural language is, into some sort of numeric representation that can be used in machine learning. All right, and then each point has a label y, and in binary classification, there's only going to be two possibilities. And we're going to refer to these as -1 and +1, or negative and positive class. So roughly, the way we can think about this is that we've got a set of points. This is going to be a two-dimensional feature space. And we're going to draw some pluses up here. And we're going to draw some minuses down here. And so each of these, again, represents one of these x's. And then whether it's plus or minus represents the label. All right, and then we're going to represent a classifier as a weight vector w. And you might see theta in some places, such as texts or academic papers. We're going to try to stick with w in this course, but again, these mean the same thing. And so the way that this weight vector leads to a classification decision is the following. We compute the dot product, or the kind of vector transpose here, of the weights and the features associated with a point, and then we ask if that's greater than 0. And essentially, the way we can think about this is that there's the weight vector points in some direction in this feature space, and then we've got this decision boundary that's perpendicular to the direction that w is pointing. So the way to think about this is any point on the top right side of this decision boundary is going to be classified as positive, because the dot product with w is going to be positive. Any point on the other side of the boundary is going to be negative. And we're not going to worry too much about what happens if you exactly land on the boundary. You need to break ties somehow. All right, so that's the basics of the kind of formulation of linear binary classification. One thing I will note is that we often see in kind of other settings here, we see a bias term b, and we are going to not use that for bias of a class. Going forward, these weights that we're going to see are functionally quite similar. So that's it for this segment.
Después mariconías que están lavados y no sé qué chuto.
In this segment, we're going to talk about an example of doing classification for sentiment analysis, and that's going to help us start to build up our pipeline for how to go from text to feature vectors, which we're then going to be able to use in a classifier and take labeled data and train a classification model. So let's start with a simple example. The movie was great. So this is going to be a positive sentiment example. So we've talked about positive and negative labels in binary classification, and for sentiment analysis, that's going to correspond to positive sentiment, meaning you like something, or negative sentiment, meaning you don't like something. Let me make this example a little bit more complicated. Would watch again. All right, so why do we think that this example is positive? Well, it has this word great in it, which is going to be a word that typically conveys positive sentiment. And we have this idea of watching something again, right? That sounds like, probably you liked it enough in order to do that. So another example. The film was awful. I'll never watch again. All right, so in this case, this example is conveying negative sentiment. We see the word awful. And interestingly, we see this pair of words, watch again. But this case, we're saying we'll never watch again. So this kind of indicates a little bit about why this task is going to be complicated, because we're going to have to think about factors like negation and kind of higher level structure and how they impact things. But the basic kinds of models we're going to look at are going to use what are called bag of words features, and we're going to get to those in a second. But those features are essentially just going to look at what words or short sequences of words are present in this data. OK, so there's going to be roughly two steps. So we're going to map from text to these feature vectors, and this is a step called feature extraction. And then given a data set of D-labeled examples, we're going to train a classifier. So in this segment, we're going to talk about the first step of this process, just how to go through this feature extraction step, and then we'll come back to the machine learning aspects of this. OK, so for feature extraction then, we're going to think about how we can turn one of these examples into a feature vector. All right, so we're just going to simplify it to the movie was great. All right, so the basic, the kind of most basic version of features we are going to use is what we call bag of words. And roughly what this means is assume we have 10,000 words in our vocabulary. So we have a list of, let's say, the 10,000 most common words in whatever language we're doing sentiment in. In this case, that'll be English. And we lay them out in a big vector. So we have the, a, of, at, et cetera. Somewhere down the line we have movie. Somewhere down the line was. Somewhere down the line great, et cetera. So there's 10,000 of these. And the way this is going to work is we're going to have a 1 in each position that the word is present in the input example, and a 0 in all of the other positions. So that is going to lead to a vector that looks like this. So we're going to have 4 ones and 9,996 zeros in this vector. All right, and so there's kind of an additional variable here, which we haven't talked, which doesn't come up in this example, but these values could either be counts, so how many the are present, or it could just be presence absence. So this is going to be either 0 or 1. And so in that count case, if we had multiple does in the sentence, we would get a count of 2 or a count of 3 in this feature vector. All right, so there's so this is the representation that we're going to use kind of going forward, and it's a fairly effective representation for sentiment analysis. I'll talk about 2 small extensions of it. One is what we call bag of n-grams. So an n-gram is just a sequence of n consecutive words. And so if we think about the 2 grams of the example, we have the movie. I'm just going to underline them so you know that they're a unit. Movie was, and was great. And if you want, you can add kind of separate start and end tokens that get kind of rolled up with these as well, but we're just going to stick with these 3 for now. And so you can build a similar kind of representation where instead of 10,000 words, now you maybe have 100,000 bigrams. And that can be your feature space now. And so that's going to allow you to capture things like if you said the movie was not great, you're going to have a bigram there for not great, and you're going to be able to use that. All right, and one other modification of this is what's called TF-IDF, term frequency, inverse document frequency. So we're not going to use this a ton in the course going forward, but I will briefly mention it. Term frequency is just the count of the term. So again, this is just the count representation from above. So if you have the twice, the term frequency of the is going to be 2. And then IDF is what's called inverse document frequency. And there's a lot of ways to do this, but roughly it's written as the log of the total number of documents over the number of documents with word W in them. And so the reason you use a representation like this is because what this does is suppose that you have a common word like the. Then the is going to be in almost every document in some kind of collection that you have. And this log term is going to be very close to 0. And so the TF-IDF score for a word is just going to be the term frequency times the inverse document frequency. And so then the is going to receive a value in this vector that's very close to 0. Whereas if instead you have a word that's very rare, like mango or something like that, maybe mango shows up 10 times in your document and actually only shows up in 1 out of 10,000 other documents that you might have. And in this case, this log term is going to be reasonably large. If you're taking log base 10, it'll be 4. And so now you're going to end up with a much higher value for that. And so it's going to emphasize words that are kind of characteristic of the particular document that we're talking about while ignoring other ones. All right, like I said, we're not going to make too much use of that, but I wanted to introduce the concept. All right, so the last thing I'm going to talk about here is pre-processing. So we talked about mapping from either words or n-grams into this feature space. But what we haven't talked about is how to go from a raw string to those words or n-grams. And so this is a process called tokenization. And in English, we often take tokenization for granted because we have spaces between words. And so so-called white space tokenization works pretty well. But there are a lot of languages in the world where that assumption is not good. And identifying what units correspond to words is actually a fairly tricky task in and of itself. But we can illustrate the challenges of tokenization or the benefits of it even with English. So let's say we have, I'm just going to look at these kind of snippets, was great versus was great. All right. If you just use white space tokenization, you end up with 2 different words in your vocabulary. So in that bag of words vocabulary, we're going to have great, and then we're also going to have great with an exclamation point after it. And so this is not great in that when we train a machine learning model, we are going to treat these as different concepts. But that doesn't seem right. I mean, really what we're doing is we're combining a piece of punctuation with the word great, and we really just shouldn't be doing that. The punctuation is really a kind of separate thing, but it just gets merged together when we actually write it down. So what a tokenizer does is it's going to take a string like this and turn it into a string with possibly some additional spaces. Another example of what these do is if you have the word wasn't, it will turn this into was and then n''t. So it won't actually rewrite the n''t as not, but it will break these up. And tokenizers will also do things like handle hyphenated noun compounds and a few other things. But primarily what you're going to see them be useful for is for kind of breaking up these contractions and handling punctuation correctly. All right, so that's one thing that we need to think about as pre-processing. Another thing and this is something we only do sometimes, is stop word removal. So stop words are generally function words in English. And the reason we might want to remove these is the same motivation as TF-IDF. These are words that sort of skew our bag of words vectors and don't actually contribute a lot to a task like sentiment analysis. Generally, the notion of sentiment comes from content words rather than these function words. So we're not always going to want to do this, but sometimes, and particularly for sentiment, this can be a good thing to do. Another thing you might think of doing sometimes is casing your data. So this might be lower casing. Again, if you're doing something like sentiment analysis, that could be a good idea. It could be true casing if you're doing something that works from raw speech data, and maybe your speech recognizer, returns just data that's all, that doesn't have any case associated with it. All right, and then the fourth thing is handling unknown words. So if you have a rare word like direct, this is not going to be accounted for in the bag of words space. It's not one of the 10,000 words in the English language, so 10,000 most common words. And so what we're going to do is we're often going to replace this with some sort of UNC placeholder. Now, for sentiment analysis, you can often just drop this word, but in other cases, we're actually going to want to make sure that we have these UNC tokens in here. And then the final piece here is indexing. And this is simply the process of taking your string, once you've done all these things to it, the tokenization, the stop word removal, the casing, the unknown word replacement, and map each either word or n-gram, whatever you're using, into the space of natural numbers. And so basically that just looks like use a map. We need to keep track of, okay, the is at position 5 in the feature space, and great is at position 247. So if you go through all these steps, you should be able to convince yourself that if I give you a raw string, then you can apply these transformations, these 5 transformations, and turn it into one of these count-based feature vectors or presence-based feature vectors, either bag of words or TF-IDF. And that's going to be the first step in our pipeline towards building a sentiment analysis system. And that's it for this segment. In this segment, we're going to talk about the basic overall machine learning framework that we're going to be applying in this course, and we're going to introduce the idea of gradient descent. So the high-level idea is that we have a set of parameters, W, to optimize. And these might be the weights associated with a linear binary classifier, or they might be something like parameters of a big neural network. We're going to assume, when we're doing supervised learning, which nearly everything in this course is, that we have access to labeled data, which is going to be in this form. So what this means is that there's D points, and each one consists of an input x, which would be something like a sentence, and a label y. And the superscript I means that that's the input or the label associated with the ith training example. So suppose we're doing classification with 10,000 features. And so W is a vector in R to the 10,000. And the way we can think about machine learning is we're searching for an optimal W. We want to find a weight vector that is going to allow us to do well at our classification task that we've got. And so we think about this as an optimization problem. We have some sort of training objective which is going to be linear over examples. And then we are going to optimize it. And this linearity is going to be important for this idea of stochastic gradient descent. So what does this objective look like? Again, to keep things pretty general, we'll get concrete when we actually see algorithms that fall into this paradigm. The objective looks like a sum from I equals 1 to d, so a sum over the training examples of a loss defined with respect to the ith data point and the weights or parameters that we are optimizing. And so roughly, the way you can think of this as, okay, for these current weights, how well is it doing at fitting this particular example? And by summing up those losses over the training data, we get an overall sense of how well does this this current weight vector W fit the training data. And what we want to do is we want to find a W that fits this training data very well. And so this leads to the idea of stochastic gradient descent. And there's a whole space of algorithms here. I'm basically just presenting the general framework so that we have the basics of the machine learning, and we can get onto the NLP stuff. But obviously, there's a rich set of techniques here in optimization that we can take advantage of. So basically, what this looks like is the following. So for a variable t up to some num epochs, for I up to d, what we do is we sample j from the interval 1 to d. So basically, we are picking a picking a data point, and then we are applying an update to our weight vector, which looks like the following. All right, and so what do we have here? We have the gradient of the loss with respect to W. So what this basically is this points towards W that give higher loss. And so because this gradient tells us, okay, if we move the current value of W in this direction, we're going to get a higher amount of loss. What we want to do is we want to subtract that. We want to move in the other direction and reduce the loss, multiplied by some step size alpha. And what this step size does is it allows us to kind of look at how far we want to move and adjust that accordingly. And so we'll be talking about the step size a little bit down the road when we actually talk more about implementing this. And then for deep neural networks, this step size parameter is fairly important. But what this gives you is the kind of overall picture of where nearly all of the methods in this course are going to fall into. And so when we talk about perceptron and logistic regression, they're both going to turn out to be instances of this framework. And so we're going to be able to understand them in that vein. And then even training super complicated deep neural networks is also fundamentally going to look like this. And so this is the framework that we're going to be taking advantage of going forward. And that's the end of this segment. in this segment, we're going to talk about the perceptron. This is going to be a basic algorithm for training a, well, in this case, we're going to look at binary classification, but training a linear binary classifier that we're going to be able to apply to our sentiment analysis example. So again, recall that a binary classifier, we were defining to have the following decision rule. And in this case, I'm going to use whether the weights dotted with the features is strictly greater than 0. And this is going to give us a decision y, which is either going to be -1 if it's less than or equal to 0, or +1 if it's greater than 0. All right, and so what we are doing is we are defining an algorithm to learn the set of weights w from a training set. So here's the perceptron algorithm. So we are going to run this for a certain number of epochs. This is typically how we use it in practice. You can also run it until it converges, but that's not going to be something we're doing much in this course. We're going to iterate through our data, and then the first step is we basically make a prediction using the weights applied to the not so greater than in this case an analysis example. So again, recall that a binary classifier we were defining to have the following decision rule. And in this case, I'm going to use whether the weights dotted with the features is strictly greater than 0, and this is going to give us a decision y, which is either going to be -1 if it's less than or equal to 0, or +1 if it's greater than 0. All right, and so what we are doing is we are defining an algorithm to learn the set of weights w from a training set. So here's the perceptron algorithm. So we are going to run this for a certain number of epochs. This is typically how we use it in practice. You can also run it until it converges, but that's not going to be something we're doing much in this course. We're going to iterate through our data, and then the first step is we basically make a prediction using the weights applied to the current example. And so again, this is going to return either +1 or -1. And then we're going to update our weight vector based on this prediction. So if ypred equals yi, so if we predicted the example correctly, we're going to do nothing. We are just going to keep the weight vector the same. Otherwise, we are going to add alpha times f of xi if yi is +1, and we are going to subtract alpha times f of xi if yi equals -1. So essentially, if we predict the example incorrectly, and it should have been a positive prediction, but it was negative, that's this that's this first else line here, then we are going to add the weight vector into, the feature vector times a constant alpha into the weight vector. And so recall that the features and the weights are in the same space. So if we have a 10,000 dimensional feature space, we also have a 10,000 dimensional weight vector, and so these things can be added together. And roughly what this is going to do is it's going to encourage the dot product of the weights and the features to be more positive on future iterations. So in a machine learning course, you can prove that this will converge if the data are eventually separable. So in the other case, the other else line, we subtract alpha times f of x if y is negative. And that's just because we want to essentially downweight the value of the prediction in the case where the true label was negative. All right, so let's see how this actually works out on an example. So we're going to look at some even more simplified sentiment examples now. Movie good, movie bad, and not good. Okay, and so we've got a value of y for each one, so +1, -1, -1. And then we have our features f of x, which we are going to represent by these columns m, g, b, and n, which stands for movie, good, bad, and not. So again, we have a bag of words feature space with 4 features here, and the value of each is just going to be the count of that word in the sentence. It's the silliest sentence ever. And so that is going to give the following feature vectors. All right, so you should be able to verify that by counting the, just counting the number of occurrences of each word, we get something like this. All right, so now we're going to start off with a weight vector w, which is going to be all zeros. All right, and now we're going to follow the algorithm. So we're going to come to this first example. We're just going to go through these examples in order. So for the first example, ypred is going to be minus.
¿Qué? ¿Entendés todo?
Ah, sí. Está haciendo acá una predicción, este es el cálculo. O sea, imagínate que vos tenés estas palabras, ¿no? O sea, estamos hablando de un text classifier, o sea, un clasificador de texto, ¿no? En este caso un sentiment analysis, ¿no? Está diciendo ahí, esto está bien, mal, o sea, cuál es el sentimiento de esta oración, ¿no? Movie good, movie bad, not good. Entonces vos tenés, por un lado, ¿no? Estos son la representación de las palabras. Vos tenés la palabra movie y good, ¿no? Que existe, ¿no? Si existe
¿Eso es un binario o es un vector? Son los...
esto es una función, ¿sí? En donde vos le pasas distintas palabras, digamos, y te las mapea a un número binario de
Es
existe esta
binario.
palabra o no está esta palabra. Fíjate que movie good, entonces movie existe, good existe, las otras no. Movie bad es movie existe, good no existe, bad existe, not no existe.
Y la X y la flechita, digamos, la X con la barra encima, ¿qué significa?
¿Esta?
Sí.
O sea, esto.
Porque yo tenía entendido que eso significa como el complemento. O
No,
el
ni.
legado.
Sí, no, o sea, vos le pasas esto a f de x y te da esto. O sea, cuando vos le pasas esto a la función, te devuelve por eso. El binario diciendo existe esta palabra o no existe esta palabra. El vocabulario, acá, o sea, esto tiene un vocabulario de 4 palabras. Movie, good, bad y not. ¿No? Que están representados por la posición en cada uno de estos. Movie, good, bad y not. ¿Ves? Sí. Y entonces, bueno, nada. Y en base a esto, tenés que. Va a tener una. Y vos también tenés acá una serie de. Un nick que son los labels. O sea, si es algo bueno o algo malo. O sea, estás haciendo un sentimiento de análisis. ¿Es algo positivo o es algo negativo? Entonces tenés un más uno menos uno. ¿Sí? Bueno, y ahora lo que tenés que hacer es, bueno. Y estas son las pesas. O sea, el peso. Ahora es 000 y es básicamente lo que te va a decir si. ¿No? El aprendizaje, ¿sí? Básicamente es el vector que vas a usar para evaluar si estos números son positivos o son negativos. ¿Sí? Entonces empezás con 000 y vos haces entonces vos lo multiplicas por todo y te va a sacar que algunos te va a dar positivo, otros te va a dar negativo. Y es cuando vos aprendés. Decís, hey, esto hizo buenas predicciones, seguí para adelante. Hizo malas predicciones, actualizalo. Y estas weights, que son por eso lo que vas a usar para aprender, van a ir aumentando o disminuyendo en base a el entrenamiento que hagas. Y bueno, nada, al final, cuando tengas las weights puestas y todo en general, vas a tener
Me sorprende que usen números binarios. Yo pensé que usaban solamente vectores y álgebra.
Están usando vectores y álgebra.
Pero también usan números binarios para representar los pesos, supongo.
¿Qué? ¿Los números binarios? Para representar si existen o no. Y pueden usar otras cosas, no necesariamente, porque también esto puede significar, acá lo que no te pone es la cantidad de palabras que hay. Porque eso también se puede significar también las palabras que hay. O sea, si esto se repite muy good, a lo mejor pueden poner un 2, 1, 0, 0. Porque se repite 2 veces. O sea, no necesariamente tiene que ser binario. Normalmente en el backup of words implica el existe o no existe. Pero también vos podés hacerlo, existen otras versiones en donde vos si querés incluir en tu
sí, pero te cambia todo el sistema, te cambia toda
función.
La representación de los números.
¿Ah?
Que te cambia todo. ¿Viste?
¿Por qué?
Si vos incluís un 2 ahí, ya eso ya deja de ser un binario.
¿Y qué tiene?
Pasa a ser un número en base 2.
¿Y qué tiene?
Que cambia todos los números.
¿Por qué?
Si no, no tiene sentido.
No, porque vos no estás usando nada que. No estás usando álgebra binaria.
O sea, son unos y
Entonces
ceros.
estás multiplicando vectores. Si los vectores son 0, 1 o 500, o incluso que en base 16, no importa. Estás usando álgebra, no necesariamente álgebra binaria. O sea, no estás dando ninguna propiedad de los binarios.
Pues entonces eso es un vector.
Sí.
1, 1, 0, 0 es un vector.
Sí.
Ok. O sea, es un vector de 4 dimensiones, se puede decir.
De 4 dimensiones, sí, de dimensiones seno. En este sentido, en este caso es 4 dimensiones. ¿Sí? Que representa todas las la cantidad de ítems dentro de ese vector.
Sí.
O sea, el n, que es la cantidad de ítems, representa el total del vocabulario del dataset en el que tenés. O sea, tenés en este dataset, que es vos tenés un total de, o sea, un vocabulario de 4 palabras. Y se representa por las cuatro que tenés.
Qué loco, vos pensás que tipo podés, o sea, entiendo que se usan unos y ceros como sí o no, pero imagínate que entre 1 y 0 tenés infinitos valores, entonces podrías con 4 espacios en el vector podés representar un montón de cosas.
Con 4 espacios puedes representar un montón de cosas. I mean, sí.
O sea, estoy tirando cosas por decir.
O sea, quiero decir
Me
sí,
parece
pero no
raro
sé,
que
no entiendo
no
qué querés decir
ponga-
con eso.
No, estoy tirando conclusiones. Me parece raro que uno ponga ahí, ponerle el coso de las flechitas, un paréntesis, algo. O sea, igual se entiende que es vector porque te ponen la rayita encima.
Sí. Estamos hablando hace media hora de que son vectores igual. O sea,
Ah,
el chabón está hablando. O sea, esto es todo álgebra lineal. Esto todo se maneja con esa álgebra lineal.
Sí, sí, sí.
No. Y es porque igual estás haciendo la primera parte, que es eso, es el eh, linear classification. Que justamente, ¿no? Todavía no estamos. Y el perceptor lo que está explicando es, bueno, cómo funciona ahora está explicando cómo funciona el entrenamiento, básicamente. Cómo es que se entrena esto.
Es álgebra lineal y un poquito de cálculo también, ¿no?
No. Por lo menos por ahora no. Después hay que eso, pero todavía no. Y estadística.
Sí, man. Estadística también.
Sí, pero ahora estamos manejándonos con vectores, ni siquiera matrices, pero bueno, estamos empezando. Pero bueno, por ejemplo, la red neuronal es básicamente se representa con una serie de matrices. O sea, una red neuronal es una serie de matrices nada más.
Sí.
Que a eso le metes el... Bueno, igual vimos que descendente, gradient descent, gradiente descendiente y gradiente descendiente.
¿Para qué?
Bueno, vos querés optimizar algo, o sea, vos querés que vos tenés, ¿no? tu función, ¿no? Va a hacer una predicción. Y esa predicción puede ser buena o mala. Vos cuando terminaste de hacer esa predicción, vos tenés... Todo esto se mantiene igual. La parte de el label se mantiene igual, la cantidad de vocabulario se mantiene igual. Lo que te cambia son los pesos. O sea, cómo vos vas a evaluar esa serie de palabras,
claro,
¿no?
eso cuando se entrena, los pesos toman un valor determinado no sé, a las entradas, ¿no?
Claro, vos tenés una función, ¿no? Que va a correr y va a decir, bueno, te va a hacer el cálculo, que esto es lo que estamos viendo, ¿no? Pero te va a hacer el cálculo y te va a dar un resultado positivo o negativo, ¿no? O sea, en caso de si es positivo o si es negativo el sentimiento, ¿no? Y vos podés entrenar y decir, esto es correcto, esto no es correcto. Cuando y vos vas a tener un test run y vas a tiene una accuracy de el 10% nada más. Y vos querés que sea mayor. Bueno, entonces vos podés decir, ok, ¿qué tanto se equivocó? Y vos podés decir, mira, o sea, y vos podés direccionar, ¿no? Para dónde optimizar para que cuando vos cambies estas weights, las cambies, digamos, porque esto es un vector, el vector que cambie justamente para
en base a los casos positivos, a los los casos en que la predicción concuerda con la verdad, digamos, ¿no?
Claro, o sea, para reducir en la mayor cantidad, o sea, cambiar los weights para reducir en la mayor cantidad posible los errores. Porque vos podés agarrar y si terminás el run, si tenés un 10%, bueno, tengo que cambiarlo. ¿En base a qué cambias los pesos? O puedes decir, bueno, lo cambio para donde sea y pones otros pesos random hasta que encuentres un peso que te sirva. Lo más probable es que no vaya eso. Entonces vos tenés que tener una forma de dirección. Entonces vos lo que haces es un gradient descent para entender para dónde está. O sea, te puedes imaginar que vos tenés todo el plano, ¿no? Imagínate todo un plano donde con todas las posibilidades y todas las weights posibles, ¿no? Y el Z es qué tan accurate es, ¿no? Contra menos accurate más va para abajo, contra más accurate va para arriba. Y vos estás en una posición. Entonces vos querés apuntar, o sea, cualquiera sea querés actualizar las weights para apuntarlo a tu máxima. Por eso,
apunta el gradiente.
Claro, imagínate vos tenés una función, ¿no? Una función que va... O sea, claro, que vos por decirte un elemento, ¿no? O sea, vos cambias los distintos weights, el X es los distintos weights que puedes tener, ¿no? Los distintos pesos que puedes tener. E Y es qué tan accurate es la predicción, ¿no?
Claro.
Vos no sabés exactamente cuál es esa función, eso es lo que querés dibujar, pero vos por imaginar, bueno, vos lo tenés. Entonces vos, cuando haces esa, vos vas a tener esos pesos, vas a hacer la predicción y te va a dar un número. Entonces, bueno, vos lo que querés hacer es, o sea, posicionarte, tratar de sacar la derivada de esa
De campo escalar.
de esa, claro, de esa función en la que estás, para decir, ok, el para arriba está para la izquierda. ¿Me entendés? O sea, aumenta el accuracy aumenta si te vas para la izquierda.
Claro.
¿Me entendés? Entonces vos sabés que el weight lo tenés que actualizar yendo para, no sé, por eso, sacándole, reduciendo los números, reduciendo los números, a diferencia de aumentándolos, no sé, ¿me entendés?
Sí.
Eso es para saber la dirección en donde vos tenés que actualizar tus weights, para darle como un foco, si no tenés que lo hacer random.
Claro.
No sé si se entiende.
Entiendo. O sea, entiendo cuál es la lógica. Lo que me da mucha intriga es saber cómo la matemática te lo dice. Tipo, qué loco, boludo. A la hora de meter las derivadas, toda la bola en el álgebra, ¿cómo es que llegas a la conclusión de que quizás haciendo eso, haciendo que los pesos se acomoden a la dirección del gradiente, básicamente, haciendo eso estás entrenando?
Makes sense igual. Creo que, o sea, es como por eso es obvio. O sea, si lo pensás así, o sea, en el sentido de vos tenés la función, ¿no? Donde hay una máxima.
Claro.
O sea, que vos tenés una función, es un tema de optimización. No, optimización.
Sí.
Viste, que vos tenés la máxima, tenés que encontrar el punto donde la derivada te hace.
Pero creo que, por ejemplo, lo que hace eso para entrenar justamente se usa la multiplicación, ¿no? La multiplicación de las matrices para entrenar. O
sea,
¿o no?
Sí, o sea, a ver.
Que luego digo que eso lleve a acomodar los pesos de modo que se acomoden con el gradiente. Eso digo yo, qué loco.
Claro, vos tenés o sea, básicamente, una red neuronal vos tenés distintas layers, ¿no? O sea, la red neuronal, imagínate, vos tenés distintas layers. Cada layer está, o sea, cada neurona, ¿no? Que es un puntito dentro de esa layer, está conectada a todas las neuronas de la siguiente layer, ¿no? Entonces, básicamente esa representación, ¿no? se puede representar en forma de una matriz. Uh-huh. Y bueno, y el neutrón contiene la neurona contiene su peso, su número, ¿no? La cantidad que tiene y el bias que, bueno, para otro, ¿no? Entonces vos podés sumar, vos podés hacer todas las multiplicaciones y hacer básicamente la serie de multiplicación de matrices es lo que te genera al final el output que querés. Vos lo que haces es, básicamente, vos querés aumentar
¿Querés un mate?
Sí. Minimizar, perdón, no aumentar. Minimizar los errores. Entonces vos lo que haces es actualizás el último numerito que te devolvió la red neuronal para minimizar los problemas, y eso después vos usás el backpropagation, que es básicamente todas esas, como están conectadas todas las layers y vos es como una multiplicación que va por toda la red neuronal. Entonces lo que te afecta a uno le afecta al anterior y le afecta al anterior y le afecta al anterior. Entonces vos haces básicamente ¿cómo se llama esto? La cadena, la regla de la cadena, y vos uno por uno actualizando todas las weights. Claro. Vos actualizas uno y como actualiza, y como depende del otro, entonces vos puedes empezar a ir uno por uno actualizándolos a todos. Esto hay lo explica re bien, boludo, el Capati, el Andrés Capati. Tiene un coso de
acá no, el hecho de que esto es álgebra de matrices y quizás derivadas no es nada más grosso que eso.
No.
Aún así, darle un sentido a todas esas cosas que son muy abstractas, porque encima estás trabajando con, si vos decís que cada red neuronal se puede representar como una matriz, estamos hablando ya de matrices muy grandes, ¿no?
Ah, sí, son enormes.
Tipo, eso ya es muy, o sea, darle una representación a eso es muy abstracto ya. Por eso digo, qué loco, ¿viste?
Es por eso que, bueno, y funciona de la misma manera que funcionan los juegos. O sea, los juegos básicamente son matrices que se multiplican.
Sí.
O sea, si los abstraes lo más posible. Es por eso que Nvidia está muy...
Puedo decir los juegos, la parte
de los gráficos, claro, es básicamente multiplicación de matrices. En paralelo. Sí.
Hace triángulos y después...
Bueno, y eso todo se representa a nivel de matrices. Entonces es lo mismo que haces para hacer esto. Entonces saltaron de una a otra así de fácil. De hacer gaming, hacer inteligencia artificial.
Qué culo.
Pero super interesting.
-1. And the reason is that we have an all-zero weight vector, so when we dot it with the feature vector, we are going to end up with a value of 0. And recall that we said that our decision rule in this case is the weights transposed with features strictly greater than 0 in order for it to be positive. So again, the ties don't really matter, but we have to define it for the purposes of this, execution. So what happens then is we update w according to the first else line here. So we're going to add alpha times the weight times the feature vector to w. And so let's just say that alpha is 1 for simplicity. And so after this first example, after dealing with this first example, we are going to have 1, 1, 0, 0 as our weight vector. All right, we come to the second example. So ypred. I'll give you a few seconds to think about it, but then I'll spoil the answer, which is that ypred in this case is going to be +1. And roughly this is because we've learned that movie is associated with positive sentiment. Okay, that's not actually right in this case, but it was a reasonable thing to learn from the first example. We don't know whether it's movie or good that's making it positive. So ypred is 1. The actual y is -1. This is bad. And so we go to that second else line down there, and we're going to subtract off the features. And so that's going to give us the following weight vector now. All right, we'll go through we'll just, the third line, again, I cooked this up so it would always be wrong. So we, again, make the wrong prediction. We're again going to subtract off. And so we end up with 0, 1, -1, -1. Okay, and so this is, no. 0, 0, -1, -1. So what we've learned at the end of this first epoch, this first pass through the data, is that bad has negative weight here, and not also has negative weight. Okay, now we're going to kind of come back around to the first example. So I'm just going to reproduce. Reproduce that down here. So this was kind of epoch 1, and this is going to be epoch 2. Again, I'm just going to rewrite the example. And it turns out that here we again screw up this first one. We get ypred as -1, and it should have been positive, so we add in the example, and then we get 1, 1, -1, -1. All right, and now it turns out we're actually good. When we go through the rest of the examples, we're going to classify them as positive, and it turns out we can keep doing this as long as we want, and we'll always classify them as positive. So the algorithm is converged.
Por último, o sea, vos haces simplemente una multiplicación, o sea, un dot product, un producto vectorial, en este caso, porque este es el simple. O sea, multiplicás la función característica por los pesos y te dan un número. O sea, más 1, en este caso, más 1 menos 1.
Claro.
Bueno, y en base entonces sabes si es correcto o no es correcto. Entonces, y lo que haces es, el cambio sería, si es correcto, le sumas el característico. Si no es correcto, le restás el característico a los pesos. ¿No? Y entonces va cambiando, va morfando, ¿no? la cantidad de pesos hasta que llega un punto en donde pones más o menos accurate, ¿no? Y eso funciona, o sea, no sé cómo, pero funciona eso, o sea, es bastante
o sea, estás haciendo un producto punto, o sea, un dot producto, ¿no?
Dot product, sí.
Un producto escalar entre los pesos y la representación de lo que vos estás evaluando, digamos.
Ujú.
Entonces, si eso te da 0, quiere decir que no tiene nada que ver.
No, si eso te va a dar, parece, te da positivo, entonces vos
Sí,
se lo
tiene
sumás
que-
al
Claro, quiere decir que tiene que ver.
Ajá.
Si te da negativo, quiere decir que
Sí.
está en el lado contrario, que no tiene nada que ver.
Si estamos hablando de de la predicción, ¿eh? O sea, si la predicción
Sí.
es correcta, entonces se suma. Si la predicción no es correcta, se resta. Y la predicción puede ser positiva o negativa, eso no importa.
Mm.
La predicción puede ser positiva o negativa. Lo que importa es si es correcto o no. O sea, porque acá estás queriendo decir, el análisis de sentimiento o sea, es negativo o es positivo. ¿Listo? La predicción puede ser positiva o negativa.
Un
Por lo que
peso,
querés saber si es una predicción correcta o no correcta.
un peso es un vector.
El peso específico no.
Ah.
El vector de pesos. Los pesos son
Claro.
o sea, es
Cuando vos,
distinto.
cuando vos te da, digamos, ¿no? Cuando haces el producto escalar entre los pesos, el vector pesos y el vector de lo que vos estés evaluando, ese te va a dar un número. ¿Eso a qué se lo restás o a qué se lo sumas?
Volvé a decir la pregunta.
O sea, cuando haces ese producto escalar te da un escalar.
Ese producto escalar que te van a escalar, sí.
¿A qué se lo sumas y a qué se lo restás?
No, esa es la predicción. La multiplicación
Ah, esa es la
de eso es
predicción.
la predicción, exacto.
Claro, es una probabilidad.
Es la predicción, sí. Depende, si es la clasificador te va a dar un 1 o un 0, porque es lo que querés decir. Si es el tema de las redes neuronales, sí, te va a dar de 0 a 1, sí.
Sí, está bien. Claro,
Y eso puede ser más o menos accurate.
En base a la predicción le vas sumando o vas toqueteando los pesos, digamos.
Sí, esta es una versión fácil, lo que
Sí.
estás haciendo es sumar y restar. Pero después con las cosas vos haces el backpack creation y toda la mano en coche.
Sí.
Con el gradient descent y todo.
¿Ya viste lo de la loss function?
Log function.
Loss function,
Loss function.
sí. Que es la función que te dice qué tanta diferencia de error hay entre la predicción y las cosas verdaderas, digamos, ¿no?
Ujú.
Eso,
Sí.
que se usa después para acomodar también los pesos.
Claro, esa loss function, por eso. Esa loss function es la función esa que te estaba hablando.
Sí.
O sea, que vos querés rayar la mínima, ¿no? O sea,
Claro,
que vaya a lo mínimo. Entonces vos una vez, esa función tiene un gráfico, whatever, ¿no? O sea, tiene que tener un gráfico en base a lo que sea que le cambies, los parámetros que le cambies, va a ser mayor o menor.
Sí.
¿No? La cantidad de los. Entonces vos estás en una sesión y vos querés irte para el lado que tenga el slope, o sea,
La menor.
el slope más bajo, más
Pico
bajo, más
mínimo.
pronunciado.
Sí, sí, sí.
¿Cómo se llama slope?
Slow.
El slope,
La pendiente.
la pendiente más baja, sí. O sea, que es más pronunciada. Porque querés o sea, querés irte para el lado donde o sea, el loss sea lo más chico
Lo más
posible.
chico posible.
Sí. Y vos pensás que, o sea, si estás con uno, o sea, solo X, o sea, si el parámetro es únicamente X, entonces, nada, te fijas para dónde está tirando para abajo y te vas para allá, ¿no? Pero vos pensás que los parámetros de la loss function pueden ser, o sea, por eso, es un hiperdominio, o sea, tenés por eso miles, incluso millones de parámetros que hay que toquetear. Entonces, saber qué parámetro que toquetear y para qué lado es complicado. O sea, si vos tenés un único input a la loss function, entonces te fijas para qué lado suma y para qué lado resta y te vas para el lado que resta, ¿no? Por eso, x, y, luego la función te vas para el lado que resta. El tema es si lo querés hacer por eso, 100.000. El input o sea, de la loss function son 100.000 parámetros, da vos a tocar cada uno de esos. Entonces necesitas una forma matemática para saber a qué dirección.
Son formas matemáticas.
Claro, para qué dirección tomar. Eso es el gradient descent.
Y cada forma de entrenamiento tiene su propia loss function, ¿no? Su propia loss function, creo. ¿Es así?
Igual eso
Eso
todavía va después. Eso te lo explico mejor cuando llegue esa parte. Porque eso es más para el lado.
La regresión lineal es una loss function, o sea.
No, No,
No es una loss function, pero tiene su propia loss function, eso digo.
No, la regresión lineal es la técnica que usas para reducir.
Sí, ya sé, boludo. Es la línea media.
Sí. Pero bueno, eso, ¿con qué te refieres con que tiene su propia loss function?
Que quiero decir, la regresión lineal te da una línea que intercepta más o menos entre todos los puntos, o sea, agarra como un medio, ¿no? Es la línea que más representa a esos puntos. Quiero decir, aunque sea la línea que más representa, hay una diferencia de error entre cada punto.
Sí.
Esa diferencia de error se puede representar como una loss function.
Sí.
Eso digo, que aunque sea que digo que eso también tiene eso.
Sí, pero no tiene nada que ver con el gradient descent.
No, pero es la forma más fácil de explicar una loss function.
Sí.
Eso digo.
Ah, ok, está bien. Pero digo, no tiene nada que ver con el gradient descent.
La regresión lineal, no.
No.
No, nada.
No, linear regression. No, sí, tenés razón. O sea, es la base de la low function, sí. La linear regression. Pasa que.
Yo creo que me vi un videito que empezaba aplicando por la log function y después decía que cada modelo tiene su propia ¿viste? Función.
Claro, vos para. O sea, sí, fair. O sea, vos para sacar. En el linear. Cuando haces linear regression es no sé, no me quiero animar a decir que es lo parecido, es lo similar, pero sí, está correlacionado con el gradient descent, sí, fair.
No sé, yo ese tema no toco.
O sea, es la técnica, la linear regression es la técnica que usás para disminuir la loss function. De la misma manera, el gradient descent también es la técnica que usás para disminuir la loss function, solamente que en distintos modelos. Vos no usás gradient descent en las neural networks. Or I think you don't. Linear regression, perdón.
No sé.
Usas gradient descent.
No sé, boludo, tipo, no sé qué es. Ya, yendo al lado de Machine Learning, no sé qué es cada cosa, por lo tanto no te puedo decir nada. Pero te comentaba eso nada más. Está muy copado porque te dice error, ¿viste?
Converged. So hopefully this kind of shows you, sort of how this works and how from this kind of data we can learn some reasonable weights here. All right, we're going to look at one more example, and then to kind of understand one of the shortcomings of this algorithm. So we're going to use the following 4, again, quote-unquote sentences. So good, bad, not good, not bad. Again, y plus 1, minus 1, minus 1, plus 1. And then here are the f of x's, 1, 0, 0, 0, 1, 0, 1, 0, 1, and 0, 1, 1. All right, so I'm just going to draw this using my three-dimensional drawing skills, which are non-existent, but and we end up with the points arranged like this. So again, this is a good kind of test for visualizing what these feature spaces look like. So because we have 3 features, we're in a 3-dimensional space, and so if we think about this point, for example, corresponds to not bad because we're kind of out at position 1 on the bad axis, position 1 on the not axis, and then position 0 on the good axis. Yeah. All right, and so what happens when we execute the algorithm? So I encourage you to go off and do this as an exercise, but you might already kind of see the problem here, which is that the algorithm will actually loop infinitely. And this is because the data are not separable. The perceptron is guaranteed to find a solution or a classification boundary that separates the positive and negative examples if one is possible. In this case, you can't do it. They're kind of on this they're sort of on this sheet that's exactly aligned with your screen, and there's no way to cut them up. So this kind of illustrates, this sort of illustrates a fundamental issue with the perceptron and unigram features, which is that they can't model these interactions between words that are somewhat important. And so the solution to this ends up being that we want to add bigrams. And so what we could do is we can expand our feature space with not good and not bad. And it turns out if we do this, I'm not going to draw a 5-dimensional space because I can't, but if we do this, the data end up being separable, and now we can classify them. And so separability is not something that we're going to think about all that much because a lot of times the data is separable because you just end up with having a bunch of features. But what this does illustrate is that by changing the underlying feature set, we're going to go from something that doesn't work to something that does work. And that is going to be a pattern that we see fairly frequently as we think about feature design problems for the first part of this course. So essentially, this shows how the perceptron works. You've seen an example of it, and we can think a little bit about how it interacts with the underlying set of features. That's it for this segment. In in this segment, we're going to look at the perceptron from a different perspective. Rather than kind of defining it as this kind of algorithm that iterates through the data and uses this error-driven update procedure, we're instead going to reframe it as an instance of stochastic gradient descent where it's minimizing a loss function. And so the place we're going to start with that is looking at what that loss actually is. So we are going to define a loss function in the vein of what we saw with SGD that is going to have a little bit of a complicated structure, but we're going to unpack it. Okay, so we have this. We have these two cases here that depend on this term w transpose f of xi times yi. This is a little bit of a weird thing. The way I want you to think about this is that basically this is 0 if w transpose f of xi is greater than or equal to 0, and yi is 1, or w transpose f of xi is less than 0, and yi is minus 1. All right, so what we're going to do is we're just going to focus on the case where yi equals 1. It ends up being kind of symmetric for positive and negative examples, but this is just a little bit easier to wrap our heads around. So it turns out we end up with a loss function that looks like this. So what I'm going to put on the x-axis here is w transpose f of xi. So I'm not defining this in terms of like some normal thing like x. We're instead looking at the dot product between w and the feature vector on this example. And the loss ends up having this structure. So the y-axis here is loss. All right, so you should be able to convince yourself that when yi is 1, again, that's the case that we're looking at here, you can kind of plug this into the equation up above, and we get these two terms. So it's 0 when this w transpose f of x thing is greater than or equal to 0. So that's the kind of flat part on the right. And then we have negative of that quantity when it's less than 0. So that gives the slanted part on the left here. All right, so I've just defined this loss function, and I guess what I'm asserting to you is that this loss function plus stochastic gradient descent is going to give you the perceptron algorithm as we saw it before. So we could do a bit of a sanity check here. So first of all, when the loss is 0, we don't make an update. So in the perceptron algorithm, we check if the example was classified correctly, and if it was, we don't make an update. In this case, when we're on the kind of right part of this graph, we've classified the example correctly, and the gradient of the loss is with respect to w is going to be 0. So that kind of tracks. And what is that gradient? So as we said, it's 0 when wt f of x I greater than 0, and it's minus f of x I otherwise. And so computing thinking about the gradient of this is a little bit tricky, but this ends up just being a linear function of, you can think about it just as essentially scalars, w times f of x. You can actually write out the dot product if that's easier for you to think about. And you should be able to confirm that when you're on the left part of this graph, and you have this minus w transpose f of x thing, taking the gradient with respect to each particular weight w gives you that corresponding feature value. And so we can just kind of batch all those up as, the gradient with respect to the vector w is minus f of, the whole feature vector f of x. If you're not familiar with vector derivatives, that's okay. We're not going to use them too much throughout this class. All right, so this is kind of encouraging in that it also lines up with the other case that we saw. So again, we're looking at a positive example here. And in the stochastic gradient descent algorithm, when we come to an example, we multiply the gradient by this minus alpha thing. And so let's say alpha is 1. What that's going to do is that's going to take our weight vector, and when we apply that gradient update, we're going to add f of x into the weight vector w, and that exactly lines up with what the perceptron algorithm is doing. So we have sort of an alignment here between this view of the perceptron and our stochastic gradient descent algorithm when we define the loss function in this particular way. So we can actually look at what this looks like on an example. So what I have on the right here is I've cooked up a small example with basically two coordinates here. So we have 4 data points. 2 are positive and 2 are negative, and they have the coordinate values as shown. And we can plot the loss value with respect to the weight vector. So what we're showing here on the left is as you change the values of x and y, which are the 2 components of the weight vector here, you incur different amounts of loss. And so that's colored with this heat map here. And the thing you want to note is that there's this kind of wedge-shaped segment here where the loss is 0. And what does this mean? Well, if we have a weight vector that's right here at the edge of the wedge, what that does is that gives you this decision boundary. I'm actually going to draw it slightly above the axis just so you can, just so you can see that it kind of exactly just sort of barely gets everything correct depending on how you break ties. And then when you have a vector that's kind of pointing out here along, if I can draw a reasonable diagonal line, pointing out here along the diagonal, the kind of perpendicular to this looks like this. And so again, you're going to kind of just barely get the sort of positives on the right side of the line. And then any other vector in the middle here works as well. All of these have loss 0. And we can look at we just kind of rotate this and look at it from another perspective, and we can see the sort of landscape here of the loss value with respect to these coordinates of the weight vector. And so the way to think about this is that gradient descent wants to move down along this loss surface. And so if we initialize the weight, the weights of change, they have so what I have on the right here is I've cooked up a small example with basically two coordinates here. So we have 4 data points, 2 are positive and 2 are negative, and they have the coordinate values as shown. And we can plot the loss value with respect to the weight vector. So what we're showing here on the left is as you change the values of x and y, which are the 2 components of the weight vector here, you incur different amounts of loss. And so that's colored with this heat map here. And the thing you want to note is that there's this kind of wedge-shaped segment here where the loss is 0. And what does this mean? Well, if we have a weight vector that's right here at the edge of the wedge, what that does is that gives you this decision boundary. I'm actually going to draw it slightly above the axis just so you can, just so you can see that it kind of exactly just sort of barely gets everything correct depending on how you break ties. And then when you have a vector that's kind of pointing out here along, if I can draw a reasonable diagonal line, pointing out here along the diagonal, the kind of perpendicular to this looks like this. And so again, you're going to kind of just barely get the sort of positives on the right side of the line. And then any other vector in the middle here works as well. All of these have loss 0. And we can look at we just kind of rotate this and look at it from another perspective, and we can see the sort of landscape here of the loss value with respect to
Mira, a ver, fíjate. Vos tenés esto del X y el Y, es o sea, tenés, fíjate que vos tenés un weight, un peso, que es un vector que tiene solamente 2 componentes, X e Y, ¿no? X e Y. Y vos tenés esta la representación de las cosas. Entonces, si vos, y después en el eje Z vos graficás la loss function, ¿no? Qué tan grande o chico de mismatch hay entre cada una. Y fíjate que hay puntos que donde vas más. Entonces vos imagínate que tenés 2 X y Y random, que te quedás acá en un punto arriba. ¿Qué haces? Entonces vos tenés que buscar la forma de cambiar los weights de manera que sea lo menor posible, ¿no? Sí. Entonces vos haces el gradient descent para saber para qué lado ir.
Ahora, hay forma de que quede perfectamente alineado, que la log function sea 0. No.
Sí, en este caso sí, esto es todo el 0. Imagínate que, por eso, en este caso, por ejemplo, es todo hay todo un rango en donde la log function es 0. O sea, por ejemplo, bueno, si vos le metés una línea acá en el medio, o sea, le metés una línea así, shack, pues tenés una clasificación completamente correcta, porque todo lo que está por abajo de la línea es menos, todo lo que está por arriba de la línea es más, y es completamente correcta. Obviamente esto es un simple, ¿no? Es un modelo simple.
Claro.
Pero sí, claramente que sí se puede.
Para mí que no. Quiero decir, sí, puede ser que haya zonas donde sea 0, pero no puede ser todo 0.
Ah, 100%.
Es un modelo probabilístico, no hay unos y ceros en la probabilidad. Es tipo, puede ser 0,0999.
No, es un modelo de clasificación en donde está todo ahí, que es, o sea, que puede encontrar, o sea, si existe que exista después en la realidad un punto, no es un modelo estadístico hasta ahora. Hasta ahora todo esto que te estoy contando no tiene nada que ver con probabilidad.
Entonces, ese modelo,
o sea, vos podés sacar cuál es la probabilidad de que dentro de exista un nuevo.
Pero vos sí, entonces, ese modelo siempre va a funcionar, una vez que vos lo calibras todo, va a funcionar siempre bien, no hay chance de que se equivoque.
No, estás, que en la forma en la que la entrenaste, si volvés a correr con el mismo test dataset, entonces te va a dar una loss de 0. Siempre vas a tener correcto.
Okay.
Ahora, después puedes poner otro dataset que es distinto al test run, que a lo mejor tiene cosas completamente distintas, y ahí sí puede ser que la loss function cambie.
Sí.
Y si pasa eso, normalmente también se llama eso que overfitting.
Yo creo que, o sea, vos para bajar esa log function tenés que iterar, ¿no? Ahora bien, ¿cuántas iteraciones tenés que hacer para que sea perfecto? ¿No tenderían a infinitas? ¿O hay un número? Yo te digo a la práctica. Imagínate que yo creo que nadie va a hacer algo que la loss function sea tan baja porque vas a gastar un montón de cálculo, ¿no?
Para eso el gradient descent, para saber para dónde ir.
Sí, sí.
O sea, porque esto literalmente hiciste un cálculo de todos los puntos.
Sí.
En la sesión.
Por
No
eso.
te, o sea, no, esto es fácil porque son 2 parámetros, pero si tenés 1.000.000 no te da el cómputo para hacer
No,
todo
no te
esto.
da el
Entonces vos
cómputo.
solamente, para eso el gradient descent, para ir directamente solamente a hacer el cómputo de los que te convienen, los puntos que te convienen. That's the concept.
Sí, está, o sea, la parte teórica hay que probarla con cosas chiquitas y después llevarlas a lo más grande.
Claro, después extrapolas y lo haces más grande.
Lo extrapolas, claro, y lo haces a escala, digamos.
Ujú.
Pero en escala es imposible que el loss function sea cero. Se me hace
No, la escala literalmente es imposible. No, que te dé 0.
O sea, si tirás infinitas veces y tienes una computadora de esa puta, llegás, pero...
Ni puta idea, no sé, sinceramente no sé. Es una buena pregunta y es.
Ah, tomá el mate, boludo. ¿Cómo le diste vos?
Te lo di yo, boludo, hace media hora que estamos.
Disculpa, estoy colgado.
with respect to these coordinates of the weight vector. And so the way to think about this is that gradient descent wants to move down along this lost surface. And so if we initialize the model to some weight point here, and then we pick up an example, well, the gradient on that example is going to somehow push us down this lost surface. Or if we accumulated the gradient over all of these examples, we would kind of directly go down along the direction of steepest descent here. And so as we kind of make our perceptron updates following this loss, we will eventually get to this kind of the sort of flat plateau region at the bottom, and that represents convergence of the algorithm. So there's this nice kind of visual intuition, I think, as well for thinking about how this loss function interacts with the perceptron training. I'll just quickly show one more example of this. Here we've removed the data point in the top right. And so the loss values are now different because we have 3 data points instead of 4, and so the kind of sum of losses over this training set is going to be different. However, the thing I want to point out is that this kind of wedge here is still the same. And the reason is because these 2 points were the ones that really kind of governed where the separating decision boundary had to be. And so the fact that we remove the other point actually doesn't impact where the optimal solutions are at all. And so I think it's just a nice visualization of, again, connecting the loss formulation of perceptron with the kind of error-driven procedure we saw before. And so we're going to move on from perceptron and discuss other learning algorithms, but this maybe helps connect possibly a version of the perceptron you might have seen before with this SGD formulation. That's it for this segment.
Interesting. Ya está por hoy.
¿Terminaste de cosas de...?